All right, folks, welcome to week 2, and this will probably go into week 3. Not that it matters to you when I've recorded this, but I'm kind of here at the church in the wee hours of a Friday morning, just getting ready. Also, one thing about this room is it is not air conditioned, so coming up here in the morning is a good idea. So I'm still waking up, got some coffee going, so we're gonna be fine. All right, time to come out in front of the camera now. And I think we're recording. Yep. So good morning, good afternoon, good evening, wherever you are. And just some preparations for this week. So hopefully at this point we've put 1 week behind us. We've sorted out some of the technical details of what we're doing in class, or if we're not really meeting in class, maybe we're doing a complete flipped inverted classroom, totally online at this point. I'm not sure. So when I recorded this, we haven't made those decisions yet because it is now Friday, I think it's the 8th of August, something like that. So a little bit before we're getting started. So a couple things to get ready for this lesson. The PowerPoint slides, especially the first slide that just has a bunch of text on it, you want to copy that down. You want to do all of that before you even get started here, because I'm not going to copy all of that down. That would be, I've put the outline here. So you want to do all those basic definitions. Those are pretty simple definitions. They're really sort of middle school physical science definitions, but they're really important. They come up all the time this entire year and really in the science curriculum. So they're really good to go back and do that. I will illustrate all of those definitions throughout the 2 lessons this week, or 2 or 3 lessons, however many I do this week. So you want those. You also want a periodic table. Not just any periodic table. I put this one online under handouts and resources or something like that. I may have reposted it for this week too. So this is the one that I would like you to use, but you really want to get a good printout of this so you can see it legibly, because we're going to label some stuff on this as we go. So that's something that you want to do. You can even color in the groups and all that stuff. Maybe you did that in high school, but this is something you'll be able to use on a quiz or a test, provided you don't put sample problems or something like that on the back. So this is the one that you will want. What else do I want to say? Oh yeah, next week there is an activity. It's pretty traditional during this section to teach a little bit of history. Where did we learn about the modern theory of the atom? Some of the famous experiments that were done. I'll talk about them some in class and on the videos, but quite frankly, we don't have enough time to go into all of that in any detail. I love the history of science. I love the history of chemistry. I'll bring in stories to kind of put it in historical context for you, because I think that's really important. But I'm not going to have time to sit here and write a bunch of notes that you can pull out of your book or watch a video on or something like that. So what I have for you, instead of listening to me talk about it, is a timeline activity called, I think it's called A Brief History of Matter and Atoms, where you go from pre-atomic theory and a little bit beyond what we call traditional atomic theory into more modern concepts, like the standard model of the atom that physicists would use. And even that model is being changed right now. So we're even not even quite completely up to date on that. But that activity is helpful for that. So that's something you can work on. That's not due till next week. Also, just a little bit of a heads up, week 2 quiz will be of more information from week 1. So significant figures, scientific notation, Greek prefixes, and unit conversions. So those topics are going to be, again, for this week's quiz, and maybe a little bit more in-depth problems. Okay, so let's go ahead and get started. So you can set up your notes. I'm going to illustrate all these definitions. And the 2 things I'm going to do in this lesson, again, are stuff you've seen. Some of you maybe just saw this last year if you just had a chemistry class and you're coming from high school. Some of you saw this stuff several years ago if you've ever had a chemistry class. So these things are going to be more of a reminder. So how do we classify matter? Pure, mixture, homogeneous, heterogeneous. These are pretty basic definitions, but they're important. And then the states of matter. So I'm going to fill in these 2, hopefully on the same board. I'll try to write legibly enough, but I'm going to need this space over here. I've got a couple better erasers, so hopefully I won't have to mess around as much with erasing the board. So today's lesson, no math, a lot of qualitative definitions, and I'm going to need to hit some coffee because, like I said, it's early in the morning. It's what's the clock say back there? It's not even quite 6 o'clock in the morning yet. Okay, so, and also, we are still in chapter 1, technically, I think. The beginning part of chapter 1, it doesn't really matter where we are. I do a little bit more with these topics in preparation for things down the line. So there's going to be some stuff in here. I don't do exactly what the book does. So I think it's important to not do exactly what the book does to move on from there. Okay, so let's do some stuff you call it. So a taxonomy. I should really probably call this a taxonomy rather than a hierarchy, because a taxonomy has a category, breaks it into two. That's, if you had a biology class, you call that a dichotomous key. Well, that's what we do here. So matter is anything that has mass and takes up space. Okay, that's the basic definition of matter that you'll see in any physical science textbook. And I have some additional information about that on the PowerPoint slides. And chemistry is the study of matter, the changes that it undergoes, the physical changes where the chemicals are still the same, they just change the form they're in, called the state, or they change their chemical nature. They become new molecules or atoms. Okay, so some chemical and physical changes, and we're going to get to the chemical changes later. Okay, so that's matter, anything that has mass and takes up space. So you've seen that definition. And either matter consists of one thing and we use this generic word particles all the time. So it's either a collection of atoms or a collection of molecules, only one thing. So it's only gold. It's only sucrose. It's only glucose, C6H12O6. So it's either pure or it's impure. I'm probably going to run out of space over there. I'll erase some of this later. So it's either pure, it's one thing, or it's a mixture. Two or more pure substances put into the same physical space. Pretty easy stuff. Good thing to know. And if it's pure, it's either an element, which you'll find on the periodic table, the PT. So, you know, it's one of those on there. There's actually, you can think about it. I think one of the homework questions asks you to do this. Where can you go into a store, a grocery store, a hardware store, a big box home improvement store, and buy a pure element? How many pure elements can you actually go out and purchase? There's a few. So an element is one type of atom. We're going to talk a lot about atoms, of course. Or when atoms bond together, we call those a compound. So there's no periodic table of compounds. That would be ridiculous. And my computer's about to log off. So a compound is two or more atoms guess I should put like a little dash there. Two or more atoms bonded together, and how they bond together is a whole other thing. Either it's a plus-minus charge, or we call that an ionic bond, or they share electrons, and you draw a little line in between them. That's called a covalent bond. Okay, so there's a lot more to the story here. So if it's pure, it's an element, or it's a compound, and I think I've got some symbols here, and we're just going to do some cartoons. This is the way it used to be done in the old days of alchemy, and it's still helpful. So hydrogen is our smallest element, and sometimes we will symbolize that. So it's not an equal sign, it's a 3 line, so that usually means to represent or symbolize by. A small dot, pretty typical to do that. Oxygen, we will symbolize by a large open circle. It kind of looks like the O, that's fine. And nitrogen, we're going to use these symbols a lot. For reasons which actually make a lot of sense, we're going to use a triangle. So hydrogen, so those are the examples of elements. I mean, they are on the periodic table: hydrogen, nitrogen, and oxygen. Periodic table of the elements. Now, if we wanted a compound, we could do lots of things here. So, you know some simple compounds. Water. So we would symbolize it like that. Simply showing the bond, physically connecting a graphic art design, very small, cheap one. And then this one. Nitrogen with 3 hydrogens. Does anybody know what that is? So it's nitrogen with 3 hydrogens. So we put it, we represent the chemical formula. By the way, these are the element symbols. These are chemical formulas: H2O, NH3, 2 hydrogens, 1 oxygen, 1 nitrogen is understood to be 1, 3 hydrogens. And this is actually ammonia. There's a more systematic name for that, but for historical reasons, that is called ammonia. So those would be examples of compounds. Okay, that's fine. I don't think I have anything there I wanted to say. Yeah, good. Okay, let's move over here to, well, you know what, I have a note down here, I'll put this down, is a lot of the elements on the periodic table exist as diatomic molecules. So there's a lot of them on the periodic table that exist. They don't exist as these individual atoms. And I'd like you to know these. So oxygen does not exist as oxygen atoms. Oxygen exists as O2. That's what you're breathing in. That's about 20% of the air that you're breathing in. Nitrogen exists as N2. That's about 80% of the air you're breathing in. Now, some people ask, why is there so much nitrogen in the air? Well, there's lots of reasons. Mainly because of bacteria that need nitrogen to survive. So most species in the world are actually bacteria. So that's why there's a lot of nitrogen in the atmosphere, if you want to talk about chemical evolution. So those are H2, hydrogen exists as a diatomic species. Chlorine, fluorine, bromine, and those are called the halogens. So know these. So when we say oxygen, we mean this. When we say nitrogen, we mean this. Hydrogen, we mean this. So these are diatomic species. So it's good to know these. So when you say the word, you're not thinking about the atom, you're thinking about the diatomic species. So I'm just tossing that one out there. Okay, oh yeah, mixtures. Mixtures are pretty much defined macroscopically, in other words, what it looks like. So good etymology here. Homogeneous or homogeneous. I hear that occasionally. It doesn't really matter to me what you call it. It appears uniform. It looks like one substance, same substance. And heterogeneous, or occasionally I'll hear heterogeneous. I don't typically see that or hear that very often. So homogeneous, when you look at it with your eye, it appears to be uniform. Maybe that's the word everybody uses. But it looks consistent. It looks like one substance. It looks like a pure substance, but it's not a pure substance. Heterogeneous, well, if it's not uniform, it's non-uniform. It's maybe not the best way to put it. It looks like more than one thing when you look at it with your eyes. And there's lots of examples here. I'm just going to put the classic examples. If you put a little bit of salt in water, the salt will obviously dissolve. I mean, if I put 50 pounds of salt into a bucket of water, it's not all going to dissolve. But if you put in some salt, so you can think of ocean water without all the other stuff floating around it. So pure salt water, that's an oxymoron. So salt water, it looks like one thing. Heterogeneous ones, the classic one there, is oil and water. Okay, these definitions are really pretty basic, but there are some things that are a little confusing. Like a compound. What's the difference between a compound and a homogeneous mixture? What's the difference between a compound and a heterogeneous mixture? Some of the homework questions ask you to make distinctions between some things that are a little more subtle than it might be. So it's really important that we have a clear idea of what we're talking about. Even in my opening announcements for this course, talking about the SARS-CoV-2 virus, nomenclature is important, even for something that seems so trivial like this. Are we talking about an element or a compound? If it's an element, is it diatomic? There's also some other exceptions to how things look, and I'm going to put those up later. I think I may put those up here shortly, actually. Or are we talking about a mixture? So, again, keep these definitions in mind. They're pretty important. Okay, so that's the basic hierarchy in taxonomy and matter. I'm going to erase a chunk of this so you can kind of get set up here. What you're going to need for this next piece is a pretty good chunk, because I'm going to make this diagram over here. So you're going to want probably the better part of a piece of paper, or a whole side of paper. Sorry, I'm still waking up here. Okay, it's not erasing fall that well, but better than it was before. Okay, I think I like the way that I do this one. You've already heard most of this stuff. You have solids, liquids, and gases, and you may have even heard what's one step, so I'm going to go solid, liquid, gas. And there's also another state of matter that goes beyond that. You may have heard of that one. If you go even higher temperature, a lot of people have heard this, so you may already have seen what's this. Okay. There's also one, more students seem to know this one. If you go beyond a solid going this direction, so you cool something down even way close to absolute zero, you get another state of matter. I'm just going to toss those in later. But for now, we're just going to stick with the simple ones. I don't think there's anything else I wanted to do. With this? No? Okay. And let's just, so these are called the states of matter, physical changes, so we're not changing the molecules, we are just changing the state, solid, liquid, gas. So we're just going to stick with something super simple, water. And we already know what the symbol for water is. I'm just going to choose an arbitrary number of water molecules. I'm going to use 6. Fun. Okay, so we're going to have a solid water, which we symbolize with an S, we put it as a subscript. So this would be H2O S, solid water. And we call that ice, of course. Then we'll move over here in a little space. So liquid, fortunately, that's also the same symbol we used for length. It's also the same symbol we used for seconds, but we put it as a subscript in parentheses. I just typically call this water, typically. And then we'll call gaseous water steam or water vapor. I think that's all I wanted to put for those. Okay, and this is a chance for me to show a lot of those definitions from the first page. Okay, let's just start left to right. I think we're ready to go here. So we're gonna, oh, by the way, what am I drawing here? Sorry, these boxes should all be the same size. I was not a very good artist. If we're gonna show 6 water molecules, just 6 of them. That's an arbitrary number. There's, of course, if you have a glass of water, there's, you can't even fathom how many are in there. We can calculate it, but it's pretty hard to imagine that. So I'm just gonna do 6. So what does a solid do? Well, a solid maintains its shape and it maintains its volume. So it's like a little molecular level ice cube sitting at the bottom. These are cross-sectional boxes, so think of this like a, well, I had to enclose the box, so when we talk about a gas, it's easier. So this is just a rigid container. Okay, so we'll use that as a rigid container with corners. Why am I saying that? Because if it was a balloon that could go back and forth, we're not dealing with atmospheric pressure right now. All this atmospheric pressure out here. So we would draw it like this. There's 1, there's 2, there's 3, there's 4, 5, and 6. Fine, okay. So, maintains, I don't think I spelled that right. That is right, okay. Like I said, it's early. So a solid maintains its shape and its volume, that's fine. And I think you know some of this, we've talked about this already. To go to a liquid, that's going to occur at approximately 0 degrees Celsius. In fact, that's when the phase change occurs the other direction too, and we call that melting. That's the phase change. And then we go to a liquid. So how would we draw this? Okay, well, basically we lose the shape, but we keep the volume. Okay? Okay, well how would we draw that? Well, we just spread it out. Takes the shape of the container. So it loses the shape. Well, what shape does it take? The container. Also, make sure you don't draw these different sizes. Like we're heating it up. Occasionally, I'll sometimes see magically students will draw water molecules bigger because they're heating up. Things expand when they heat, not on a molecular level, on a macroscopic level. Some things do, not everything. So that's what we would draw there. That's fine. So here we maintain shape. Oops. I just said the opposite. Maintains the volume. Takes shape of container. There's good lab notebook maintenance. If you make a mistake, don't scrawl it out. Just draw a line through because you'll be using a pen. Okay, I think that's right. Fine. Let's keep going. Heat it up even more. To go to a gas, you know that that's going to occur around 100 degrees Celsius. And we call this boiling. Now, boiling occurs, the technical definition of boiling is when the pressure of the gas pushing up equals the atmospheric pressure pushing down. And there's an equilibrium between those two. That's called the boiling point. The other way to take something from a liquid to a gas is something called evaporation, which is different. Evaporation is actually molecules in the air colliding with the surface and picking off the molecules and kicking them up into the atmosphere. So I'm not making that distinction right now. So there are two ways that we can go from a liquid to a gas. You can boil it, or it can evaporate if you simply expose it to the atmosphere. But here, I'm not exposing it to the atmosphere, just making the point. How do we draw these? Well, we've added enough kinetic energy, I'm going to make some notes about that, to these molecules, so they've pulled away from the intermolecular forces holding them together, and they've been liberated, if you will, released into the container. And what happens there is they take up the shape of the whole container, but not physically with the water molecules themselves. The container is still mostly empty space. But what the water molecules now do is they spread out and take up the whole volume that they occupy. Looks like I'm drawing this kind of symmetrically. I really shouldn't be doing that. 1, 2, 3, 4. Okay, we got it. And they're in constant motion. So we have more molecular motion as we go this direction. And sometimes in graphic novels or comic books, you'll put these little swishy lines. I forget what those are called. Every year I say that. I never remember to look it up. It shows they're in constant motion. They're constantly colliding with one another, and that's what we call gas pressure. Okay, so here, occupy the entire volume of the container. So it doesn't have a shape anymore, it just takes the shape of the container. And I think that's all for that. Okay, and then, okay, we can also go the reverse direction. If you go from a gas to a liquid, think about that for a little bit, that's called condensation. And if we go from a liquid to a solid, what we call that freezing. It's also sometimes called fusion. We'll talk about that in the lab a little bit more. And also there's occasionally some times where, I'm going to draw this on the bottom because I'm going to need the top for something else. Yeah, normally I put this at the top. There's actually some certain cases where you skip the liquid state. It goes directly from a solid to a gas. So you get, there's some circumstances where that happens. Dry ice, which is carbon dioxide, is the classic example. A lot of students recall when you skip the liquid and go directly to the gas, that's called sublimation. The one that's not as common, but it's actually pretty important, is going from a gas to a solid and skipping the liquid phase. That's kind of interesting. You have a gas and it goes like onto a surface directly as a solid. Does anybody know what that is? There's no hands out here. That's called deposition. The gas molecules are depositing themselves onto a solid surface. This is how computer chips are manufactured. So actually there's a lot of, what am I looking for here? Advanced manufacturing techniques that involve deposition techniques where you're taking a gas and you're sputtering it onto a surface in an ultra clean environment to do something high-tech like electronics. So it's more of an engineering thing, I suppose. So those are the definitions, those are the states of matter, but I also want to illustrate a couple of those definitions from the first slide. I'm going to need a little bit more space, so I'm just going to erase the headings here. And this will be it for this lesson, so it's mainly okay. All right, so when we're going in this direction, the water molecules actually have to absorb energy. Oh, by the way, capital E is an abbreviation for energy. So when you go this direction, this is endothermic. So endothermic is when you absorb energy. Exothermic is when you give off energy. We'll get to that. So these are endothermic physical processes. Again, a physical change is when it's still water, it's still H2O, it's just S, L, and G. It's not like we're taking the water and converting it into hydrogen and oxygen separately. That would be a chemical change called electrolysis, which we're going to use as an example in the next lesson. And then also there's some other definitions we can build in here. So it's endothermic going that direction, it's still a physical process. We're also increasing the kinetic energy. Kinetic energy is the energy of motion, so we're imparting more kinetic energy onto the molecules as we go from solid to liquid to gas. And we're also increasing the temperature. And actually, I think I put this on there, on this first slide. Temperature is an indirect measure of kinetic energy. And the Kelvin temperature scale is directly proportional to molecular motion. The Celsius scale sort of is, but it's still based on the freezing point and boiling point of water. So that's that direction. Well, the other direction, the first law of thermodynamics, also known as conservation of energy, you cannot create or destroy energy, you can merely change its form. So if it's endothermic in a physical process in this direction, it has to be the exact opposite in this direction. You only have two choices, typically here in these cases. So in this direction, it's going to be exothermic. Well, it's also physical. You can write out the word exothermic, that's fine. And you're going to have a decrease in kinetic energy and temperature going this direction. So it has to be that. It's just kind of bizarre because you freeze something, that's exothermic. Normally you think, well, when you freeze something, it gets colder. Well, yeah, but in order for it to get colder, it has to release that excess energy to get to the solid state. So it takes a little bit of time to think about that. I don't think, the other information that I have is on the slides here. So sorry, I'm just gonna cheat and look at the slides. So that's B and C. Yeah, that's B and that's C. And I'm not sophisticated enough to have good. And I'm going to go to D later. I'm just going to make some comments here. So the other two states of matter, they're on the slides. They're kind of cool. If we keep going in this direction, eventually the water molecules will break apart. And if you keep going even further, the atomic structure will actually break apart, and you'll have basically this swirling maelstrom of nuclei and electrons that aren't attached to anything. That's called a plasma. Lightning is the most common example of plasma that's out there. If you keep going colder and colder, closer to absolute zero, you see the image I have on the slides. The molecules actually don't do these experiments with molecules, they do them with atoms. The atoms cease to become individual entities and they sort of morph into a superatom, and that's called a Bose-Einstein condensate. If I remember right, the atoms on the periodic table that they've done experiments with Bose-Einstein condensates tend to be the noble gases because they don't react with each other very much and they can lose their individual identity. I think xenon was one. If you want to Google that, Bose-Einstein condensates and what atoms did they use to make those superatoms, you can do that. But you should know that you've got your, if you keep going, which I don't have a picture for that. Those are called Bose-Einstein condensates if you keep going down here. And plasmas if you keep going up here. I think I heard of another state of matter that somebody proposed recently, but I can't remember what it is. So maybe somebody, if you want to post something about that, or send me a note, I can add that in later. Okay, so that's going to be enough for one lesson. The next one, if you want to get ahead of yourself here, we're just going to jump in with letter D and talk about chemical changes. So we'll use some of these symbols to talk about chemical changes, and we'll get there. So some of the same stuff. Okay, that's it.